That video is probably the most advanced piece of the tutorial you can ever see on that channel. Prepare the code you will see in today's tutorial wasn't really so obvious. It's a lot of tutorials in internet which not explain all in so explicit and understandable way. I hope I will explain it today for you more understandable, because topic we are talking about is not so obvious and really complicated. And if something will be not so understandable for you in that video, I will not explain something. Please ask your questions in the commentary. I will try to answer them if I could. Also, despite of all my research I did, I still totally not feel like an expert in that field. If you also can add something from your knowledge that I will not mention in that video, I will be also grateful for that. So let's start. As I shown in previous video, the local large language models could be successfully used as brains of the robots when our robot need to make his mission in some place where is no access to internet and no any ability to connect to ChatGPT, for example. And local model that could be run on some microcomputer on that robot, even on the Raspberry Pi, could make really unstandard decisions in unpredictable environment. Basically, that robot could think about his actions before doing it. But problem with small language models like Zephyr 7b I shown you in previous video, that they not really clever. It's a really huge difference between intelligence of GPT-4, for example, and such 7b models like Zephyr. There is big problem because the decisions they generated is not really optimal and not always clever. But hopefully there is one little trick we can do here. Basically, the top large language models like OpenAI GPT-4 or some models from Anthropic are good on doing a lot of things. They doing good translations, they doing good decision making for Mars rovers, and not only they doing good being a chatbot, but local LLMs, even when not so clever as GPT-4, could gain some expertise on doing one concrete task and do that task good, even have comparable quality of responses with GPT-4 while doing that task, and totally not comparable while doing all the other tasks. So in that video I will show you how to fine-tune your model to make it an expert on being Mars rover brain, and we'll see if our fine-tuned model will make better decisions than normal Zephyr we have seen in previous video. And also I hope if we'll succeed with this, maybe we will be able to shorten the time of execution, because as you remember, we need around 8 minutes to wait for the model response when running it on the Raspberry Pi. Now, when we don't need to provide any instruction to the model, only provide the context what it can see around, because all the instruction is already provided to the parametric knowledge of the model, means saved in that neurons. So maybe because of the shorter instruction, our model will be also work faster. Let's see. First step in the fine-tuning of our local LLM is the simplest step, but a little bit tedious, is gathering, basically creating the data for our fine-tuning. To make it work, we need to create JSON-L file with our training data inside of it, which in my case looking that way. We have a bunch of JSONs with input parameter that had our observations of space around our Mars rover, from clear, right clear, left some rocks, rear also something. Also writing here if container is empty or full, and the direction to our base. That's all you remember from previous video. If don't, I invite you to watch it also. Okay, and another parameter of our JSON is output, which is also JSON, with same as in previous video. Output includes reasoning that describes how does our LLM should think. So first of all, it tells that container is empty, and because of that we need to continue exploration. After that, it thinks about possible direction to go and choose the better way to move. JSON also had direction field with final decision of our LLM where to go. So in case of that example, we decided to go front as there is probably clear space and it's good terrain to go. So we need to create a bunch of such JSONs. In my case, I had 100 of examples. First, I tried with 50 and it wasn't really work. It was too small. Till 100 examples is also, I think, small, but it already somehow works. I think if you want to have really production results, good results, predictable, the number of examples should be even bigger. But it's also all depends on your case. So, one practice to create an examples in easy, well, relatively easy way is to use some more clever model that will generate examples for our 7B less clever model. And in practice, that most clever model almost every time is GPT-4, just because it's for now the most clever model available. You can see here my conversation with GPT when I first described him a problem that we creating data for a fine-tuning of our Mars rover, and here rules of the game are described. So if container is empty, rover should explore, when full it should return to base, blah blah blah. We have some different types of terrain: clear space, low rocks, high rocks, dust clouds, craters, and short description for every one of them. Is it possible or not, or how risky it is to go the terrain, which terrain to prefer over which terrain. And also writing here that sometimes it could be mineral and our task is to collect it. Next, I providing it example about how his generated data should look like. Again, you can see input, output, reasoning, blah blah. Also pointing his attention about providing good reasoning here, and also asking him to write relatively short reasoning, because as we know, GPT very likes to write long text. Next, we can see that GPT generated some responses. So basically, when it generates the responses here, you still need to check all that responses carefully. Basically, GPT makes a lot of errors, and when even it's the most intelligent model here, still you need to check it out. You need to sometimes rewrite that reasoning, rewrite his decision, and so on. So really careful here. After that, I am asking him to continue, asking about some improvements. For example, to not write in quotas around the examples, just write them one after another. He provided more examples. Again, I need to check it out and ask him to continue, blah blah blah. Here you can see, for example, that I asked him to introduce craters, because on the all previous examples he just forgot about existence of the crater. Like he randomly provided different terrains, clear space, dust clouds, high rocks, didn't provide any crater. Here it started to provide it. Again, in another iteration, I need to remember him rules of the game and preferences about the types of terrain, because he had a lot of errors with that, and ask him to provide some more tricky, complicated examples. So examples with no clear space visible, only with harder types of terrain. After that, I'm asking him to provide some another types of examples, and basically, problem with it, his examples are not really random. He has some biases, preferences. So after that, to make that input data more random, I came with another idea. I asked him to generate a Python script that will automatically generate input data. You can see that script here. Input data generator, which chooses random direction, random type of terrain, random container status, adds mineral sometimes or didn't add it. With that approach, data is generated really randomly, and the task of our GPT after that is just provide responses for already generated data. Maybe let's run the script to show you how it works. And you can see that it generated 10 of examples of input data. So basically copying that examples here, we can see that GPT generates outputs for our provided input data.
Still here we need to look at him and really check it out if he writing reasonings right, and very often to manually rewrite that reasonings. But well, at least our inputs really random, and as I said in previous video, if we can do something programmatically here, let's do it programmatically. Okay, so after that you collected let's say 100 examples for our fine-tuning JSON file, and also we need a couple of examples. In my case it's 20 of them for validation JSON. The data is basically needed to measure performance of the model on different training steps. So well, our data is ready. Let's go to creating and fine-tuning script.
Today we successfully created datasets for our training and validation for our model fine-tuning. And although I planned first to create one single video about all the fine-tuning process, I just realized there's too much material to show, and it will be better to separate it for few different videos. In first one we just made the data preparation, and in the next one we'll create a fine-tuning script and we'll finally fine-tune our model. See you next time.